Module 4, Big Data Querying with Hive. This module introduces the Hive programming framework and how it can be used to build big data solutions. This module contains the following topics. Topic 1, Introduction to Hive. Topic 2, Representing Data in Hive. Topic 3, Hive Data Types. Topic 4, Probing Data with Hive Queries. Topic 5, Hive and AWS. Topic 6, Use Case, Ad Hoc Analysis and Product Feedback. By the end of this module, you will be able to discuss how Hive can be used for data querying, describe the options that are available for creating a big data solution using the Hive programming framework, explain the difference between joins in MapReduce and joins in Hive, understand how Hive is used in business use case scenarios. Hive is an efficient data warehouse infrastructure that allows for querying and analyzing of large data sets. Hive lets anyone who is already fluent with SQL leverage the Hadoop platform without the need for writing complex programs. This data warehouse infrastructure works on top of the Hadoop framework, letting users manage and query unstructured data as if it were structured. Hive uses MapReduce for execution and HDFS for storage, so the ability to achieve massive scale and fault tolerance are innate features of Hive. Hive is designed to enable easy data summarization, analysis of large volumes of data, and ad hoc querying. Hive provides a simple query language called HQL, or Hive Query Language, which is very similar to SQL. HQL is easy to use, especially for people who already know SQL. Hive provides some key features. Extensibility, including pluggable MapReduce scripts in the language of your choice, rich user-defined data types, user-defined functions, and ETL or extract, transform, and load database functions. Hive provides interoperability by providing an extensible framework to support different file and data formats, and finally, Hive offers enhanced performance by leveraging the Hadoop framework. Hive has different subcomponents that communicate with the underlying Hadoop framework as a single unit. For user interfaces, Hive provides both a command line interface and a web user interface. Hive also provides APIs, or application programming interfaces, such as JDBC and ODBC. The diagram shows the different components that constitute Hive architecture. Click each tab to learn more about Hive architectural components. The Metastore stores the system catalog, which contains metadata about tables, columns, partitions, and so on. This information needs to be rapidly served to the compiler, so it is stored in a traditional RDBMS. The driver controls the lifecycle of a HiveQL statement as it moves through Hive. The driver also maintains a session handle and session statistics for query processing. The query compiler parses the Hive query. It compiles HiveQL into a directed acyclic graph of MapReduce tasks. In simpler terms, the compiler converts every query into a MapReduce task and generates an execution plan with the help of table and partition metadata from the Metastore. An optimizer handles optimization tasks on the chain of transformations it encounters. Operations like column pruning, partition pruning, and repartitioning of data are done by the optimizer. Pruning is a technique used to reduce the execution time. The execution engine performs the tasks from the compiler-created execution plan in proper dependency order. The execution engine interacts with the underlying Hadoop instance. The Hive Thrift Server is an optional service that exposes a very simple client API to execute HiveQL statements, allowing a remote client to submit requests to Hive. The Thrift Server is a framework for cross-language services, where a server written in one language like Java can also support clients in other languages. This makes it easy for applications developed in multiple languages to use Hive. Let's look at the Hive query processing workflow. Initially, the compiler is invoked by the driver when it receives a HiveQL statement for execution. The compiler translates this statement into a plan, which consists of a DAG, or directed acyclic graph, of sequentially ordered map-reduce jobs. The driver then submits the individual map-reduce jobs from the DAG to the execution engine. Hadoop Hive and traditional RDBMSs, or relational database management systems, were built for different purposes and have their own pros and cons. Hadoop is not an alternative for a traditional RDBMS. The two can coexist in one system. Just like the old saying, use the right tool for the right job, specific job or project requirements will drive the decision as to which option to use. Typically, programmers prefer procedural programmatic approaches for accessing and manipulating data like Hadoop and MapReduce. On the other hand, non-programmers typically prefer declarative manipulation languages such as SQL. Hadoop Hive is a SQL-like language and includes MapReduce functions in RDBMSs, making it easy for non-programmers to use. Notes: unlike Hive, relational database management systems do not scale with the size of the data. RDBMSs can handle high and low latency SQL queries that need to analyze structured data in terabytes. On the other hand, Hadoop Hive can handle high latency queries that process petabytes of multi-structured data. This means that Hive would not be appropriate for applications that need very fast response times. Some key features that differentiate Hadoop with Hive and RDBMSs are as follows. Hive can handle petabytes of unstructured data, while most RDBMSs can handle terabytes of data and can only handle structured data. Hive is open source, flexible, evolvable, fast, and still evolving. Most RDBMSs are proprietary and have defined constraints. Hive supports distributed architecture, while RDBMSs support client-server architecture. Hive can run on commodity hardware, while RDBMSs used in data-intensive applications typically need high-end servers. As such, Hive can lead to reduced infrastructure costs, while RDBMSs costs increase as the size of datasets increases. Hive is read-based and therefore not appropriate for transaction processing that typically involves a high volume of write operations. Traditional features like transaction management and ACID principles for data reliability are key benefits of traditional RDBMSs. ACID stands for atomicity, consistency, isolation, and durability, a set of properties that ensure that database transactions are processed reliably. In this topic, representing data in Hive, you will learn about Hive CLI, or Command Line Interface, how Hive data is organized, Hive Database, tables in Hive, views in Hive, partitioning in Hive, bucketed tables, Hive Metastore, indexing in Hive, archiving in Hive, and storage types. Hive provides traditional command line access. The command line interface is the most common way to interact with Hive. Hive CLI is a default service. CLI can be used for issuing DDL, or Data Definition Language, and metadata exploration commands such as create tables, inspect schema, query tables, and so on. To see basic usage and help, run the following command. Here is an example of running a query from the command line. Here is an example of dumping data from a query into a file using silent mode. Click the button to see CLI options. Data is organized in 4 different categories in Hive. They are database, tables, partitions, and buckets. Click the buttons to learn more. The database consists of the namespaces that separate the tables and other data units to avoid name conflicts. Tables are homogeneous units of data which have the same schema. Each table can have 1 or more partitions, which determine how the data is stored. Note that a table can have a partition column. Partition columns are different from the data columns, and they are not actually stored with the data. They are virtual columns. They are not part of the data itself, but are derived on load. Data in each partition may in turn be divided into buckets or clusters based on the value of a hash function of a column in the table. For example, the page views table might be bucketed by user ID. With Hive, a database is essentially just a catalog or namespace of tables that helps avoid table name collisions. Hive databases are used to organize production tables into logical groups. Note that the keyword schema can also be used as an alternative for database in all the database-related commands. A key difference between a Hive database and a traditional databases lies in their schema policy. Traditional databases follow a schema on write policy. Once a schema is designed for a table, while writing data, it checks whether the data to be written conforms to the predefined schema. If it does not, then the write is rejected. The opposite is true of Hive. Hive database follows schema on read policy. Data written to HDFS is sent through without any gatekeeping rules or constraining checks. Rules are applied when we want to read the data rather than pre-configuring the structure of the data ahead of time. There are numerous advantages to using Hive database. You can load your database into HDFS before you decide what to do with it. The schema can evolve as time goes on, since you don't have to know everything at the outset. Hive database allows the flexibility of having 2 different schemas present on top of the same underlying data set. And the original source data format can change. With Hive, creating and managing databases is easy and similar to SQL. Click on the buttons to view syntax examples. This is the simplest syntax for creating a database called employee. The if not exists command is useful if you want to avoid generating errors if a database with the same name already exists. In Hive, data typically resides as flat files in HDFS. A Hive table is a logical concept that is made up of a number of files in HDFS. In simpler terms, tables are just files stored in subdirectories in HDFS. There are 2 kinds of tables in Hive: internal managed tables and external tables. As the name suggests, internal managed tables exist in HDFS, and Hive controls the entire life cycle of their data. Hive stores the data for these tables in a subdirectory inside a warehouse directory. With internal tables, the data and table are tightly coupled. When an internal table is deleted, both table and the data, including the metadata, are deleted by Hive. External tables reference remote data that is stored outside of Hive. With external tables, there is no need to move data into the Hive warehouse directory. The schema and metadata are loosely coupled with the actual data. With external tables, when a table is deleted, only the metadata gets deleted. The actual data is left untouched. This is like deleting a shortcut icon for an application on your computer's desktop. External tables come in handy when data is going to be used by multiple databases or when you need multiple schemas for the same underlying data. A good example would be analyzing data from stock markets. The same data set will be used by different tools and might be analyzed concurrently under different schemas.